Good morning and welcome to the next class of this postgraduate video course on advanced hydrology. In the last class, we started a new chapter on unit hydrograph. We looked at the basic definitions, the basic concepts of linear systems theory, the hydrologic system model, and then we looked at a general model proposed by Chow and Kulandaswamy in 1971. Then we looked at the basic two principles of linear systems theory, which allow us to compute or make certain applications in complicated situations, and these were the principles of superposition and the principle of proportionality. Then we said that we need to understand three basic functions, and then we started looking at the first one, which is called the unit impulse response function. We defined the unit impulse response function as a function or a response from a system when it is subjected to a unit impulse input. And what is a unit impulse input? A unit impulse input is nothing but an input of unit amount which is applied to a system instantaneously. Okay. So, you have certain forcing function or certain force being applied to a natural system instantaneously, all right, momentarily, and then it is taken off, and then how the system would respond, the response is then called unit impulse response function. What was the first one? We said it is an example of a guitar string, in which if we provide a certain force using our fingers to a guitar, then we get a response or the sound waves in the form of a impulse response function. Then we said another example was of shock absorbers of an automobile, in which we said that if the system is the shock absorbers of a car, the force applied is, let us say, passing of the car over a hump or over a speed breaker or a pothole, then that acts as an impulse input to that system, and what comes out, the response of the shock absorbers is expressed as the impulse response function. Okay. We also said that this impulse response function also follows the principle of proportionality and the principle of superposition, because this is also based on the linear systems theory. All right. That is where we stopped, and today we will start by looking at a third example of a catchment, all right, which is also the we can apply what is called this impulse response function. All right. The third example which we will look at starting with today's lecture is of a catchment. Okay. What happens in a catchment when a unit amount of rainfall or 1 centimeter of or 1 inch of rainfall is dumped onto the catchment instantaneously? What will come out of that is actually called the unit impulse response function. All right. So, when 1 centimeter of effective rainfall is applied on a catchment, the response how in terms of your DRH or the direct runoff hydrograph, all right, the response from the system, and the system being your catchment, is described by a unit impulse response function. Okay. How does it look like? We have seen this earlier, but we will look at it again today. So, this is your 1 unit of 1 centimeter of rainfall. What comes out is your u t minus tau. Okay. So, this is your time domain, and this one is your q t, or I should say u t t minus tau, and the input is applied at time tau, and we are calculating or we are expressing the response after some time, or the delayed time is t minus tau. So, that is how this unit impulse response function is defined. Okay. Now, this input which we have seen is instantaneous. All right. The way this unit impulse response function is defined is that this 1 centimeter of rainfall is applied instantaneously. Okay. However, in reality the rainfall does not occur instantaneously, all right. It does take some time. Like for example, you may have certain amount of rainfall occurring in 1 hour, 2 hours, 3 hours and so on, all right. So, how do we determine or how do we find the response from a catchment, all right, using this impulse response function, okay, or the unit impulse response function for a continuous output, all right. So, for a continuous input, I should say, which is your rainfall, all right, we can use the unit impulse response function to calculate the response in terms of the DRH. Okay. Well, how do we do that? Let us say that this is your time domain and you have some continuous amount of rainfall like this, okay, and this we are saying is your intensity of rainfall represented by I tau, all right. So, we say that let your I tau be the rainfall intensity in let us say centimeters per hour or some suitable units during d tau, all right, and this d tau is very small time interval, very extremely small, so that we can say that its duration can be neglected or infinitesimal or very small. Okay. So, I tau is the rainfall intensity during some very small interval d tau, and what is this d tau is nothing but infinitesimal time interval. In hours. Okay. All right. So, if you are looking at it like this, let us say you have this, all right. So, this curve is what? It is nothing but the intensity as a function of time tau, all right, and let us say that this is your time tau and this is your time d tau. Okay. So, we are looking at this strip of input, okay, which is occurring almost instantaneously during interval d tau, which is infinitesimal or very small. Then can you tell me what will be the depth of rainfall input during this very small infinitesimal input d tau? What will be the depth of rainfall? Okay. You know the intensity, you know the very little duration, all right. So, what will be the depth of rainfall? It will be the intensity multiplied by d tau, the duration. Okay. So, you can say that this is going to be equal to your I tau times d tau during your small interval d tau. Okay. Now, we have the instantaneous input of the magnitude I tau d tau, right. Now, how can I find the response from the catchment in terms of DRH from this input I tau d tau? Assuming I already have the unit impulse response function. So, now we are looking at the using of the unit impulse response function to calculate the total response or the total DRH, all right. So, this will be, let us say, let us define it first, let the DRH resulting t minus tau hours later, okay, from this input. What input? This one, I tau d tau. Okay. Let us say that this is equal to small q of your t. Okay. What will that be? I can use the principle of proportionality. I know what is the ordinate of your response from the catchment due to this 1 centimeter of rainfall. All right. So, given your u t minus tau, I can multiply each ordinate by the amount of rainfall, and the amount of rainfall is I tau d tau. Okay. So, it will be equal to what? I tau d tau. Okay. So, this is the amount of rainfall multiplied by your u t minus tau. All right. This, let us say, is given to us. All right. This is your unit impulse response function. And what is this q t? This q t is the response from this system due to this infinitesimal strip of your rainfall, which is expressed by this. Okay. All right. So, now I have written the expression or calculated the response from this very small input I tau d tau, which occurs in d tau. All right. How about, how can I now calculate the response from the total rainfall input? Now, this I tau is continuously occurring, and I have calculated the output due to this small strip. So, what I can do actually is, I can divide this whole input into various strips, small strips, and then I can integrate the whole response. All right. So, I will have very small discrete intervals. All right. Again, this is an assumption or simplification. All right. So, I can divide this whole input into small strips of inputs, and then I can integrate, so that I can calculate total response from this continuous input. Okay. All right. So, what does that mean? That the total response, let us call that as q t, due to the total input or the complete input for the whole domain, total input function I tau, all right, can then be found by integrating the response q t. Okay. So, mathematically you can write it as q t is equal to integral between 0 to t of what? Of your small q t dt, right. So, what you are doing is, you have these small strips between times limits 0 to t, just before that rainfall. All right. So, what you are doing is, you are integrating. So, let me go back here and try to demonstrate. What you are doing is, you are integrating up to certain time. All right. So, you have all these strips, this one, this one, this one, this one, and so on. So, you are integrating over this whole time for the whole input, and this you can continue for the whole time duration. All right. So, this is your total response. All right. Now, q t we have already written from this equation. This whole expression is your q t. So, if you put it in here, what will you have is this integral 0 to t of your I tau u t minus tau and d tau. I am going to number this equation as 7.2.1. Okay, and let me put it in a box also, because this is a very important equation, which is called the integral form of convolution equation. All right, extremely important result, which allows us to calculate response, DRH response from a catchment for any complex rainfall event. Okay. So, let us say that this is called convolution integral. Convolution integral and is the fundamental equation for solution of a linear system on a continuous time scale. Okay. It is called convolution integral, all right. Integral because that integration process is involved. So, you are summing up certain response, and convolution is just a term which is used. Why? Because this function is giving you the convolution, or you have the input being applied to a system, that input is being convoluted, all right. It is being transformed through that system to create that output response, all right. So, this whole process of convolution which involves lots of processes in the catchment, okay. It may be translation, it may be attenuation, and it may be many other storage effects or characteristics. So, all this convolution process actually is taking care of the transformation of this effective rainfall into direct runoff hydrograph, all right. That is why it is a very important tool for us. Once we have developed this unit impulse response function, then we can find out the response from any continuous input of rainfall. Okay. All right. So, now what we are going to do is, we will look at this process of convolution in a graphical manner that will probably clear this whole thing a little bit better. All right. So, let us look at the convolution in a graphical form. Okay. All right. So, this is your tau domain. We are talking about the input. All right. This is your rainfall input, as we have said earlier. This is tau, this is d tau, all right, and this is your rainfall input. Okay. Now, when does the response from the system will start? Due to this input, all right. Obviously, it will be after this time. Okay. So, let us see, then you say you have this response starting from here. This is your t minus tau domain. Okay. So, you have any general time t, all right, any general time t, but you are subtracting tau when the rainfall has actually occurred. Okay. Now, this curve is what is your u of your t minus tau, all right, and let us say that this is your unit impulse response function. So, what is this? This is u t minus tau, all right. What does that mean? If you take the ordinate of this curve, what are the coordinates? Well, this is t minus tau is the x coordinate or the time domain, all right, and what is this? This is nothing but this, all right. So, this curve is your unit impulse response function, which we know. And what is the objective of the convolution integral? Well, the convolution integral uses this unit impulse response function and applies the series of these rainfalls, all right, small strips, and convolutes all of that through the catchment to give you a combined response as per the equation 7.2.1, okay, which is this equation. Okay. So, we are looking at the expression of this equation 7.2.1 graphically. All right. Okay. All right. So, your response will actually start from time t is equal to 0 when this rainfall starts. So, obviously, you have a strip here and the response will start from here itself. Okay. So, this is your time domain t. All right. What is this? This is your qt. Qt is what? This is equal to your direct runoff hydrograph due to all of this input. All right. What is that input? This whole input. Okay. All right. So, I am just going to draw this DRH. Let us say it will be looking like this. Okay. And if you take any point on this curve, what is this ordinate going to represent? This ordinate is obviously your qt, which is equal to what? Which is nothing but 0 to t of your the equation 7.2.1, which is the convolution integral I tau u t minus tau d tau. Okay. This is your convolution integral. Okay. So, what we have is this is the input falling on the catchment. You are using the unit impulse response function, which we already have, let us say, and then the final output then is given by this curve here. Okay. So, this is called the process of convolution of your input, which is your effective rainfall, which is continuous, or let me say continuous effective rainfall, all right, through the catchment to produce response in terms of the DRH. Okay. This is an extremely important process. All right. It is the basis of all of your rainfall runoff models. Okay. Now, I am going to ask you a very simple question, okay, which is related to what we have just seen, and you have seen all these concepts in your earlier classes. Okay. It is just that we are looking at them in a most general form. All right. And the question is this unit impulse response function. Let me try to show it to you, this whole thing, this whole guy here. What is this? Have you seen it earlier? What is this? Physically, it is representing what? It is the DRH from the catchment when the catchment is subjected to 1 centimeter of rainfall occurring instantaneously, right, not in any duration, that duration is extremely small. So, the response from the catchment when it is subjected to unit input or 1 centimeter of rainfall occurring instantaneously is called what? It is nothing but instantaneous unit hydrograph. Okay. Have you studied IUH? I am sure some of you may have. All right. So, this whole concept which we have seen is nothing but the IUH, which is your equivalent to unit impulse response function. Okay. All right. So, this is about the unit impulse response function, and for analyzing various situations in the catchment, as far as the hydrograph analysis is concerned, we need to understand two more different types of functions. Okay. And what are those? Well, first one is the unit step response function. All right. And the other one is the unit pulse response function. So, let us start looking at these two functions now. So, we have seen unit impulse response function. The next function we are going to look at is the unit step response function. Okay. The second one is unit step response function. Okay. Let me just give you the schematic. What is a unit step response function? Well, it is nothing but the response from what is called a unit step input. Okay. You have the unit step input which is being applied to your system, okay, which is a catchment we are going to look at, and then this models that as a reservoir, and what you have is the unit step response function is coming out of it, and this is denoted as G. Okay. So, in words, if you want to write it, let us first define what is this unit step input. A unit step input is what? Is an input that increases from a rate of 0 to 1.0, all right. So, from 0 to 1 the rate, all right, at time 0 or initially in the beginning, all right. What does that mean? Instantaneously, all right, and continues indefinitely or continuously thereafter. Okay. All right. So, what kind of an input is this then? If you want to draw this, this is your time domain. So, this input is 0 at the beginning, and then it quickly reaches some rate of 1, and then it continues indefinitely, all right, it is continuing. So, this amount is 1 centimeter per hour or 1 or unit input, all right, this whole thing, and this is occurring continuously. Okay. All right, and then the output from the system is then called your unit step response function. Okay. So, what is this unit step response function? It is the response from a catchment or output from a system when that system is subjected to a very special type of input. And what is the speciality of this system or this input? It is the rate going from 0 to 1 at the beginning at time t is equal to 0, all right, and then continuing indefinitely or continuously infinitely. Okay. So, what will happen? What kind of curve do you see? All right, you will have a curve going up and then coming down? No, because the input is not stopping here. Once the input stops, that is when the DRH response starts to come down, right. Here the input is not stopping, it is continuous. Therefore, your curve will be an, or the response will be an ever rising curve, all right. So, the response would be something like this, all right, and this we say is called GT as a function of time, which is your unit step response function. Okay. Now, how can we find this GT or this unit step response function? Okay. Let us say you have the unit impulse response function, all right. Now, the next question is, I am going to pose this to you, how to find GT knowing or given u t minus tau. What is u t minus tau? We have just looked at, it is unit impulse response function. And what is a unit impulse response function? Well, you have unit amount of rainfall or unit amount of input occurring instantaneously, and the response is u t minus tau. Now, what we have is an input which is continuous of certain rate, all right. What will be the response from that, knowing u t minus tau. Okay. All right. So, what we can say that this q of t or the response from this input is equal to what? We can use the convolution equation or integral form of the convolution equation with what? Your I of tau is equal to what? What is I tau? It is the rate of rainfall. And what is the rate of rainfall here? It is 1 or unity. Okay? Or I tau d tau is equal to 1, which is 1 centimeter per hour. Okay. All right. So, you see that to calculate the response or the unit step response from the catchment when it is subjected to a rate of 0 to 1 occurring indefinitely will be equal to what? You use the convolution equation and you put intensity is equal to 1. All right. All right. So, what is this? That means what is q? Q is nothing but your g. This is equal to what? 0 to t. What was your convolution equation? Well, it was I tau u t minus tau d tau, right. And what we are saying is that this is equal to 1.0, right. So, what is this equal to then? This is nothing but 0 to t of your u t minus tau d tau. Okay. Or let me say that this g of t is 0 to t u t minus tau d tau. Okay. So, this I am going to define a number as 722. Okay. Now, what I am going to do is slight mathematical manipulations, because you have t and tau, both of the time domain appearing here in the integral. All right. You have t and tau as both of them. So, what we will do is we will get rid of these two and convert this equation into a single time domain, so that we can integrate it properly. All right. So, to do that, you say that let some new parameter or variable L is equal to t minus tau. All right. So, that what is dl? dl will be equal to what? It will be minus d tau, all right, because you are integrating with respect to tau here, all right. So, your dl is equal to minus of d tau. Then you need to change this limits of this integration, all right. Limits of integration means what? These limits. Okay. So, if you work on them, then you have tau is equal to 0, all right. This is with respect to tau, and tau is equal to 0. The lower limit would mean what in terms of L? Well, this is 0, L will be equal to what? T, isn't it? Okay. And for the second case, your tau is equal to T, which is the second limit, this one, all right. When tau is equal to T, you put T in this equation, means L is equal to what? L is equal to 0 from this equation, right. So, in this one you put t is equal to 0, you have L is equal to T, the lower limit, and the upper limit from this will be L is equal to 0, all right. So, that once you put this whole thing into 7.2.2, then what you will have is your g t is equal to d tau is negative. So, I will take the negative outside, integration limits are from t to 0 now, all right, and then u of your t minus tau is what? It is L, and d tau is minus d L. Okay. So, that is what I have got. That means your g of t is equal to what? Minus you can take inside and change the limits of integration, 0 to t of what? ULDL. Okay. So, you see we have done slight substitutions, some mathematical manipulations here to arrive at this equation, which is 7.2.3 I am going to number. Now, what does this equation represent? G of t is equal to integral from the limits 0 to t of what? ULDL. What is u? U is nothing but your unit impulse response function. So, G is nothing but the cumulative of your u curve or unit impulse response function curve. All right. So, mathematically you can say that, or in words, the value of a unit step response function what is that? GT, right, at any time t, all right, equals what? Equals the integral of the unit impulse response function, which is u. That is UL in this case, up to where? Up to that time t. Okay. So, this G is a mass curve of u curve. All right. Now, can anybody tell me what is this curve? If you come here, this one, have you seen this in your UG classes? I am sure you have. This is nothing but your S curve or S hydrograph. Okay. So, the first one we have looked at is IUH and the second one is the S curve. All right. We will look at the third one, which is called the unit pulse response function. The third function we will look at is what is called unit pulse response function from a catchment. Okay. We are going to represent this by H of t. Okay. Again, looking at the schematic first, you have what is called a unit pulse input. Okay. What is the unit pulse response function? Well, it is the response from your system, which is catchment, all right, in the form of UPRF, okay, and that is your H of t. Okay. So, a unit pulse response function is what? It is nothing but the response from the system when the system is applied or is subjected to a unit pulse input, right. What is a unit pulse input? Let us look at that. So, we have defined different types of inputs here, and this is the third one. A unit pulse input is what? Is an input of unit amount, not the rate. All right. Unit amount means 1 centimeter of rainfall or 1 inch of rainfall or 1 millimeter of rainfall in this case, and effective rainfall we are talking. All right. So, a unit pulse input is an input of unit amount occurring in duration delta t. Okay. We are saying duration delta t means what? It is occurring in certain finite duration delta t. It may be 1 hour, 2 hour, 3 hours and so on. It is not infinite small, it is not extremely small. So, it is not instantaneous. All right. It is certain duration of rainfall. Okay. So, this is your definition of the unit pulse input. All right. And then we want to find out what is going to be H. Okay. So, now we have the amount of rainfall is 1 centimeter and it is occurring in time interval delta t. So, what will be the rate of input or rate of rainfall? Can anybody tell me that? It will be what? 1 centimeter of rainfall occurring in how much duration? Delta t duration, all right. This is, let us say, your centimeter per hour, that is the rate or the intensity of rainfall, okay. All right. And it is occurring for what duration? Let us say tau is your input domain, input time domain, for how much time? Delta t and 0, okay. So, your rate of input is what? It is 1 over delta t centimeters per hour for time between 0 and delta t, and what is the input elsewhere? Elsewhere it is 0, all right. So, this is your unit pulse input, okay. And now we want to find out the response from this kind of input, okay. So, you have a rate going from 0 to 1 by delta t, all right, and then continuing for certain time delta t, all right, and then becoming 0, okay. Now, knowing the first two functions, that is your unit impulse response function u and the unit step response function g, okay, how can we find this function h, which is your unit pulse response function, all right. So, what we will do is we will take the earlier functions and then apply our linear system theory, proportionality, superposition and so on, okay. Once we do that, we should be able to find out what is this h, all right. So, let us look at that first. The unit pulse response function h produced by this input. Which input? This one, which we have just defined, all right, can be found or described by the two linear system principles, all right, cited earlier, okay. That is proportionality and superposition. Okay. All right. So, what I am going to do is I am just give you a step by step procedure for that first, and then we will see graphically how we can deduce this h or the unit pulse response function. All right. So, the first step is by proportionality response to a unit step input of rate 1 by delta t. What is the rate? Well, we just said it is 1 by delta t beginning at time 0, all right, or at the beginning is what is found, which will be what? Nothing but 1 over delta t multiplied by what? The step response function g of t. Okay. So, we are using the principle of proportionality. You know the unit step response function g, let us say, that is given to us. That is the g of t is what? It is the response from the function due to what? Due to an intensity of 1 centimeter per hour, all right, but it is a linear system. So, we can get the response from the system when the intensity is not 1, but x, all right, and that x is 1 by t here. So, all we do is we multiply this G by 1 by delta T, which is the intensity of rainfall, all right, for how much? For certain time, okay, only delta T, all right. So, this is what we do, that is the first step. Then what do we do? We say that if a similar unit step input began at time delta T, all right, which is the duration, all right, instead of 0, okay, its response would be what? It would be lagged by interval delta T, isn't it? Because the input has started delta T time later or delta T hours later. So, the response will also start, or it will be lagged by delta T, right, and would have a value of what? 1 by delta T multiplied by what? G lagged by delta T, okay, all right. And then what you do is the third step, then we use the superposition. How? We subtract the first or carry out this subtraction operation first minus second, all right. That is, this is the first one and this is the second one. So, we have two responses, one is G T 1 by delta T G T, other is 1 by delta T G T minus delta T, all right. So, if you subtract or carry out this operation, all right, that will give you what? That should be your H of T, all right. Let us look at this graphically. What we are saying is, let us say this is your time domain, all right. Then what we said is, we are using G of T at time, this is time T is equal to 0, all right, and what is this? This is 1 over delta T, okay, and this is occurring indefinitely. And so on, all right. The response from this is, first one is 1 by delta T G of T, all right. Now, what I do is, I am not plotting the response here, all right. Then you take a time interval, how much? Delta T, all right, and let us assume that another rainfall starts at this time indefinitely. I am plotting it just below this, but it at the same scale, just keep that in mind, right. This is also, this intensity is also 1 over delta T, but this is occurring what? Delta T later, all right. So, what you do is, this is 1 by delta T G of your T minus delta T, that is the input, and then there is a response from this in terms of this hash curve, other one is this, all right. So, let us say this is the first one and this is the second one, G of your T minus delta T, and then there is 1 upon delta T, of course, all right. Okay. Now, what we want to find out when we are talking about this unit pulse response function. What is the unit pulse response function? Well, it is the input which is going from 0 to 1 or 0 to 1 by delta T actually. Here it is. I would like to draw your attention here, this one. It goes from 0 to 1 by delta T and it occurs for duration delta T, all right. So, you come here down here. So, you want to find out what will be the response from the system due to only this input, right. What is this? This is your nothing but 1 by delta t centimeters per hour occurring for what? For a duration delta t. Okay. So, what we have done is we have 1 by delta t occurring indefinitely at time t is equal to 0, the second one occurring indefinitely starting delta t hours later. So, if you subtract the response from the first one and the second one, all right. So, if I did this one minus that one, all right, that will be what? That will be the response due to which input? This input. Do you see that? All right. We are using the principle of superposition, all right. The first one is response due to this, second one will be the response due to this, all right. So, you subtract this one from this, what will you get? You will get the response due to this guy here, which is of intensity 1 by delta t, and it is occurring for duration delta t. Okay. So, this you can then say will be equal to what? This I can say is equal to h of t. Okay. So, this is your unit pulse response function, and I am going to say that this is 7.2.4. Okay. All right. Moving on, then you can define your h of t is you can take 1 by delta t outside, and then you have g t minus g t minus delta t. Okay. This you can represent in terms of u. We have already found out what is g t. G t is nothing but integral between 0 to t of what? U L d L. We have just said that. Similarly, what will be this guy here? It will be minus 0 to what? 0 to t minus delta t, isn't it? All right, whatever is in the brackets here. Okay. So, that will be the limits of your integration of your U L d L. Okay. What is this? Using your knowledge of integral calculus, you can say that this is 1 over delta t of what? You have integral, you have one integral going from 0 to t, other going from 0 to t minus delta t. So, essentially what you have is t minus delta t to t of your U L d L. Okay. And let us say this is 7.2.5. Okay. All right. So, we have derived these this equation for the unit pulse response function, all right, and we have used the two basic principles of linear systems theory, which is proportionality and superposition, both of them, all right. In the first one, if you look at this equation, what is this telling us physically? Well, what it is saying is that your h is nothing but what? The derivative of your g curve. Okay. So, what is the h curve? H curve is nothing but the derivative of the or the slope of the g curve. So, you have the g curve or the unit step response function curve, all right. You differentiate that with respect to time, each time step. What you will get? The curve you get which describes the slope of g curve is nothing but your h, all right. Similarly, h is also equal to this equation 7.2.5. What is this telling us? Physically, your h is equal to what? It is nothing but integral of your u curve, which is your unit impulse response function, all right, between the interval. What is that interval? Delta t. Okay. So, you see that this H is nothing but your unit hydrograph, all right. So, if you remember what is this, it is nothing but your unit hydrograph. Okay. The way we have defined this H or the unit pulse response function, it is due to the unit pulse. What is that? 1 centimeter of rainfall occurring in duration delta t. What is a unit hydrograph? 1 centimeter of rainfall occurring in duration d, all right. So, it is the similar concept. So, that is your unit hydrograph, and unit hydrograph is equal to what? Well, it is nothing but the derivative of your S curve. What is the S curve? S curve is the summation of the unit hydrograph, all right, for certain duration. Okay. But theoretically, this unit hydrograph is nothing but your integral between the limits of t minus delta t to t of your IUH. Okay. So, what we have seen is that then H of t is equal to the derivative of S curve, that is number 1, and this is also equal to the area under your IUH curve between the limits of t minus delta t and t. Okay. So, basically what we have done today is we have looked at these 3 very important functions, all right, unit impulse response function, unit step response function, and unit pulse response function, all right. These are the 3 basic concepts which are your the instantaneous unit hydrograph, the S curve, and the unit hydrograph, all right. They are all related to each other the way we have described or we have derived all these equations. In the next class, what we are going to do is we will look at what is called the discrete convolution equation, and we will look at the unit hydrograph the way we have seen them earlier, all right, the basic definition, and look at some examples. Okay. So, I would like to stop here today, and then we will continue further.